Two vertical flat plates are located within a tank of water at 25 Celsius. They are sufficiently far from each other to consider the system as a non-enclosed one. So, if it's a non-enclosed space, what do we know about their boundary layers? They are not interacting, right? Each plate is 30 centimeters in height, and both plates are held at 65 Celsius. You may assume the boundary layer thickness, D, is given by the equation below. There is no initial flowing water. So this is your fine print to tell you that this is not forced convection, right? There's no external force, there's no initial flowing water, everything is still, therefore, everything that will take place in this problem will take place due to natural or free convection. Okay, so we have a little equation there. What is this equation saying? It's saying that the distance of the boundary layer, so remember the boundary layer, so if I have a flat plate like so, our boundary layer will have a certain distance from here. This boundary layer, remember the definition of the boundary layer, that how the temperature is 99% that of T infinity. So that D there is this distance, right? The distance from the plate to the boundary layer, from the hot surface or the cold surface to the boundary layer. Then L is our characteristic length. In this case here, it is the length of the plate, L. Then we have Prandtl, our old friend Prandtl, and Grashof, our new friend Grashof. So if we can calculate the distance of that boundary layer of this specific situation by relating Prandtl and Grashof. We are to determine Grashof number on one plate. It's easy enough. Determine the minimum spacing that would be needed for these two plates so that the boundary layers do not interact. And answer how we would analyze this problem differently if we knew the boundary layers were interacting. Okay, so I drew my beautiful drawing here with a tank of water. Okay, tank of water. And inside the tank of water, I have my two vertical plates. One plate, both plates at 65 Celsius, 65 Celsius. And they are both like so. And we know that because the water is at 25 and the plate is at 65, we know that there will be energy flowing from the plates to the water. Okay, so let's just do a little thought experiment. If my boundary layer, let's just draw a cube to simplify this. That's why I had the cubes there before. Let's say my boundary layer goes all the way to the tip of this arrow here for the right hand plate, and for the left hand plate goes to like so. Okay, if the boundary layers quote unquote touch each other, then by definition we don't have an enclosed space anymore, right? And the question is asking us what has to be the D. So let's actually change this to the more appropriate letter, which is delta. What has to be the delta of these plates so that these guys do not touch? What is the minimum spacing? Let's call it F, just to have another word, another letter. What's the minimum distance between these two guys, F, so that the two spacing these are not touching each other? Okay, starting off with Grashof number for one plate. So we have only one plate. We only have one plate. It's at 65 and not all that. It has 30 centimeters in height, which is the characteristic length of a plate. And our temperature, bulk temperature, T film temperature, is 25 plus 65 over 2, right, which is 35, 45, which is 45 Celsius. That's 90 to 45. Okay, so I'm grabbing the properties. As per usual, I'm grabbing the properties at 45. So let's go ahead and write down the properties. K at 45. This is for water, okay? So this is table A. 9, as opposed to A5. 0.649 watts meters Kelvin. This guy, 6 times 10 to the minus 4 seconds. Prandtl. old friend Prandtl is 3.9123. Knowing it there. And our new friend, the thing, which is this big chunk here, CP divided by this, divided by conductivity, is 4.4 times 10 to the 10. Again, I didn't do any math, okay? This is the way it is shown in the table. We need to calculate Grashof. Well, we have a fluid, we have water, right? That is our fluid, water. We don't have an ideal gas, we have liquid. So if we go ahead and do beta equals 1 over 45 plus 273 to have it in Kelvin, that won't work. And that's tempting, but you can't do that. And that's exactly why we have this guy here, right? So that we can find our Grashof without relying on that beta there. So Grashof, if you guys recall, actually, let me do it differently. Grashof, let's do it that way. Grashof equals our big friend. Let me call this guy theta. Equals theta times our characteristic length to the third times delta t divided by Prandtl. Right? And that comes again from the table. You can check on your table, on the table A9 on the right, on the header of the table. Okay, so that means that if I multiply what I have for theta, which I already have, this number here, by my characteristic length, which is 0.3 cubed times delta t divided by Prandtl, I should get my Grashof, which is part A of the problem. Okay, so 4.4 times 10 to the 10, 0.3, the third. Delta t is, what is it? 65 and 25. 65 minus 25, so that's 40, divided by my Prandtl, which is 3.9123. So Grashof is 1.23 times 10 to the 10. Okay, double check your math. Back me up, please. So that's part A. So that's one of the answers looking for. A. Cool. Next part. What is the distance, right? What is the distance? That distance F. That's what this part is asking us. What is that distance F? This was Grashof number. Distance F. Minimum spacing that we will need so that the boundary select do not interact. So let's first find out what is the D, and I'm going to go ahead and call it delta for each of these plates. Okay, so for that, I just need to literally plug in the equation. So the equation is a very friendly equation. Let me see if I can do this. There you go. Just copy paste from the previous, from the equation given in the question. Okay. So we have Prandtl, we have Grashof. We have both these things already. So if we're looking for this guy here, we just need to plug in the numbers, right? So my delta divided by my length of the plate, which is 0.3 meters, equals, by the way, we actually need this number here so that we have a unit, right? Because if you think about it, all these guys here are non-dimensional. So if we didn't have this L divided, our distance delta would be non-dimensional, which wouldn't make sense. Okay, moving on. 3.93, Prandtl 3.9123 to the minus half or minus 0.5, 0.952 plus 3.9123, 1/4 or 0.25, and Grashof, big fellow, 1.23 times 10 to the 10, and that is to the negative 1/4. So that means that my delta in meters, because I put this guy in meters, is, what was it? 2.8 times 10 to the minus 3, which is obviously same as 2.8 mils. Okay, so the question is 2.8 mils. The question was, how far apart do we need to place these plates so that they do not interact? So let's grab our drawing. Let's grab our drawing and let's answer that question. Let me zoom in. What we're saying is that this distance here, shouldn't have deleted that. Just get rid of one of them. The distance of one of the plates is 2.8 mils. Okay, so if we don't want the two plates to interact, then we need to put F will be just 2 times that, right? So F will be just 2 times distance for them not to interact, which is 5.6. Right, so as long as they're 5.6 millimeters apart, the boundary layers should not interact, which would allow us to have a non-enclosed space interaction. Right, now if we're actually designing this experiment and we are building this and we do these calculations, we know there's a lot of approximations involved and a lot of empirical relationships. So we probably play it safe and put them 10 mils apart, right? Because like in a lot of things in engineering, we use this to have a sense of direction, a sense of magnitude, and we know, okay, it's somewhere around 5.6 mils, the boundary layer for one of these plates. So if I place them 10 mils apart, this would definitely be enough for the boundary layers not to interact. Of course, you might be constrained by budget and things like that, but it shouldn't be a problem. Okay, so B, the distance between the two for them not to interact has to be 5.6 mils at least. So probably flip that, at least 5.6, right? And let's finish off with the part C. Part C is asking us, how would you analyze this problem any differently if you knew the boundary layers were interacting? So let me go ahead and pause the video and wait for you guys to answer it back. So let's go ahead and write it down. So, see? Becomes a vertical enclosed vertical plate situation, and then we have to use the correlations accordingly. Right? So, questions from your